Okay, so let us start. Last class we talked about uh, something called sequences, right? So I gave you examples of sequences and I gave you what do we mean by sequences. So today what we are going to do is we are going to see some of the properties of those sequences. So first thing is, let's start with an example. Right, so let me say in right, so if I give you a sequence like this, right, n plus 1 over n, right? So obviously, if you write these numbers down, you can see it is 2, 3 over 2, 4 over 3, 5 over 4, like that, right? So this is how the sequence, the components of the sequence will go. So here you can see that when n is increasing, the numbers are decreasing, right? Starting from 2, it is going to down to 1.5, 1.33, 1.25, and then further down, right? So it's going down. So it is decreasing, you can see. Similarly, some other sequences, they may increase, right? So they might increase as well. So now the question is, if the sequence increases or decreases, then we have to think of where will the sequence go, right? So if we increase the number n, right, we have to figure out where the sequence will go. Right, so where the sequence will go. Right, so let's see plotting these values in a picture. Just roughly, right? So when n is equal to 1, is 2, right? 1. And then at 2 is somewhere here. Let's say this is 1, then it will be 2.5. At 3, it will be 1.3. At 4, it will be 1.5. Right? So like that, you can plug it here, right? So 5 will be there here, right? So it's go like this, right? So if we join these lines, I can see that the dotted lines, right, is the line which joins the points, right? So which are plotted in the sequence, right? So here basically this is xn and this is n. So you can see that when n goes to infinity, right? When it keep on going, the sequence is going towards to some value, right? So in this example, you can see that it is going towards right. So it is going towards 1, right? So here you can see that it is going towards 1. So how do we formally define this, right? So the idea of defining this is, so when you look at the tail of the sequence, right? When you look at the tail of the sequence, right? When n goes to large and when n becomes large, right? What we do is we draw a tube around 1, right? So let us think of drawing a tube around 1. If the tail goes inside the tube, right? The tail goes inside the tube, then we can say that the sequence is converging towards 1, right? So you can make the tube as small as possible, right? So the radius of the tube, we name it epsilon, right? So we already see that epsilon is the notation we are using for very small quantity, which we can choose as small as possible. So here, if you put a tube of radius epsilon around 1, right, at the and if the tail of the sequence goes inside the tube, then we can say that, oh, the sequence is converging towards 1. So how do we formally write it down, right? So let me write down the definition of the limit. Right, so the sequence is said to have a limit L, right? If the limit as n tends to infinity, right? If for every epsilon positive, there exists n belongs to natural number, capital N belongs to natural number, such that xn minus L absolute value is less than epsilon for every small n greater than n. Right, so we write down this pictorial interpretation in mathematical notation, right? So if you say 1 is the limit L, right? For every epsilon positive, because you can choose epsilon as small as possible, there exists some n after some point. That is why the tail comes, right? N becomes very large. So that means after in the tail, right? The distance between the point xn and L, right? So here these dots are the xn's, right? These dots are the xn's and this line is L. So the distance between xn and L is smaller than epsilon. Then only the tail will go inside the tube, right? Distance between the sequence value and the limit absolute value, because the distance might be, the difference might be positive or negative, but when you put the absolute value, it becomes distance smaller than epsilon. That means the tail goes inside the tube for every n greater than n, right? So that means for every n after that large n, that is in the tail goes inside the tube. So this is how we define the limit, right? So now let's see a few examples. Okay, so we write okay, we write it as xn limit n goes to infinity is equal to L. So here you know this, right? So from A levels, you know this limit of 1 upon n as n goes to infinity is 0. You know that, right? But you have to prove it here. Here in this case, right? So we have to show that. So let me write it down. The limit is given, right? So you have to prove it, right? If you want to prove it, then what you have to do is you have to show 1 upon n minus 0 is less than epsilon for all epsilon positive and for all n greater than some capital N, right? So you have to prove it. So let me show you in this example how you can prove this, right? This is what you are doing in this first year course, because this limit you already know, right, from your A level. So here basically you are doing the proper mathematical proof, like logical, right? So okay, by definition, this is what you want, right? You want for every epsilon positive, there exists a natural number n such that 1 upon n minus 0 is less than epsilon, right? So this is what you want. Okay. So rough work. Let me write the rough work here. Just to tell you what we are doing. So basically you want this, right? Epsilon is your choice, right? You can choose epsilon as anything. So you don't need to worry too much about what is epsilon. Epsilon is your choice, so you can choose. But you have to find some capital N, right? You have to find some capital N, that is the work you have to do. And then you have to make sure 1 upon n minus 0 is less than epsilon for all n greater than n. So basically, you want this, but that is same as 1 upon n less than epsilon for all n greater than n, right? So for all n greater than n. This is what you want, right? 1 upon n, because 1 upon n is positive, minus 0 is 1 upon n, that is positive. So you can remove the absolute value. So basically you want to get 1 upon n is less than epsilon for all n. Okay. So in other words, what you want, 1 upon epsilon is less than n for all n greater than n, right? So this is what you want to get. 1 upon epsilon is less than small n for all small n bigger than capital N. So this, in other words, you want this, right? So 1 upon n less than capital N. Right? So if you show that 1 upon n is less than capital N, then for any n greater than n, 1 upon epsilon is less than n. So you can go back. So the idea is you want to find the capital N such that 1 upon epsilon is less than n. This you can do that because in chapter 1 we studied something called Archimedean property. So again, you recall that we are going back to what we learned in chapter 1, right? So we are using Archimedean property. So epsilon is your choice. Right? This is a rough work, just to work out what you want to do, right? So you can do it in your mind and write it down. Just for the notes, I am writing the rough work as well, just to explain you what to do. And you don't need to show that in an exam, right? You can directly write the proof like this. So let epsilon be positive and arbitrary. So any small positive number. Then 1 upon epsilon is positive and 1 upon epsilon is basically a real number. You all know that, right? So by Archimedean property, you know that there exists a natural number that 1 upon epsilon is less than, and this is what Archimedean property says, right? This is what the Archimedean property says. But you know, for all n bigger than n, right? 1 upon epsilon, or you don't need to write this line. You can directly go to the first line because you know the idea. Right? You can directly say that for all n small n bigger than n, absolute value of 1 upon n minus 0 is actually 1 upon n because all are positive numbers. So that is smaller than 1 upon capital N, right? But from Archimedean property, you know that 1 upon capital N is smaller than epsilon. So now since epsilon is arbitrary, right? Since epsilon is arbitrary, you can say for every epsilon positive, there exists a natural number n such that 1 upon n minus 0 is an epsilon for n greater than n. Right? So that is the definition of limit 1 upon n is equal to 0 as n goes to infinity. Right? So that's not a big thing to do. Only thing is you just need to figure out how to apply the Archimedean property. Right? So as long as you are good, you can apply the Archimedean property directly and show that this is the limit. Right? So this is how we prove the convergence. Now let me give you a few example exercises to work out. The ideas are always how to find the natural number, right? So the guessing of limit you all know, right? So you can figure it out, right? So by dividing top and bottom by an n, you can see that it is 1 upon 2, right? So here we are not going to teach you about the guessing part, right? Which we assume that you learn from A levels. So here we are just showing you how to prove it, right? So this part as I leave it as a homework. Right. Okay, let me do. Okay, so let me do another type of example. So this I leave as a homework because you can use the same procedure to find the show that the limit is 1 upon 2, right? So you have to do 1 of n over 2n plus 1 minus 1 upon 2 is less than epsilon. That is what you want to find, right? So you can choose the capital N in such a way that this inequality holds, right? So that is the idea. You can work on your own. Now, so here in these sequences, you can see that these are finite numbers, right? 0, 1 upon 2, 1, 5. All these numbers are there, so you can easily figure it out, right? So, but there are sequences which cannot have finite limit. That means they may go to infinite limits. Right? So I will write them as an exercise again, but I will show you one part, right? Okay, so we will show the following do not have a finite limit, right? So one is minus 1 to the power n. Second one is n. Right? So if you write down the sequence, you can see that they will not converge to some value, right? So these sequences do not have a finite limit, right? They may have some infinite limit or they don't have limit, but at least you can prove that they don't have a finite limit, right? So this idea of defining the limit is basically for the finite limit, right? This for every epsilon positive there exists n with natural numbers at that xn minus L less than epsilon for all n greater than n is basically a definition for the finite limit, right? So now we are going to show that these don't have a finite limit. And so if you want to show that something do not have a finite limit, the easiest way is to use a contradiction, right? So we assume that they have a finite limit, and then we will show that there is a contradiction, right? So that is the idea. I will do 1 and 2. I will leave it as an exercise. Okay, so first one, assume right a finite limit. Okay, so you assume that the sequence this has a finite limit. So the thing is, you know that, right? So then for every epsilon positive, there exists a natural number such that minus 1 to the power n minus L is less than epsilon for all n greater than n. Right? So this is the definition for finite limit. If you assume that this has a finite limit, then this relationship holds. So epsilon is anything. You can make your choice of epsilon as anything. So let me choose epsilon is equal to half. Right at the end of the solution, I will tell you why we choose epsilon as half. Is there any other choices for you for epsilon? Those things we will discuss after finishing the solution, right? Finishing writing the solution. But at this moment, let us choose epsilon is equal to this, right? Okay. So for this epsilon, right? For this epsilon, you see that. So there exists some n1 because this n, you see that by Archimedean property, basically depending on epsilon, right? So in the previous example, when you see that you choose capital N in a way that said that 1 upon epsilon is less than capital N, right? So the choice of n depends on epsilon. So here, because you fix an epsilon, right? Epsilon is equal to 1 upon 2. So we have a fixed n, right? So n1 belongs to natural number such that minus 1 to the power n minus L is less than half for all n greater than n1. Okay. So you have this. Okay. So this is how you rewrite the definition, right? Because you fix epsilon now. So you fix the capital N as well. Right. Now you see that minus 1 to the power n, right? So minus 1 to the power n has a special property that it will take plus 1 when n is even, and it will take minus 1 when n is odd. That is something you all know. So this gives me two inequalities, right? Because minus 1 to the power n minus L is less than half for every small n bigger than capital N1, right? That inequality holds for 2n1 because 2n1 is obviously bigger than n1. So minus 1 to the power 2n1 minus L is less than half. At the same time, 2n1 plus 1 is also bigger than n1, right? So you will know that. So minus 1 to the power 2n plus 1 minus L is also less than half, right? So this is what? This is an even one. So it is 1 minus L is less than half. And this is minus 1 minus L is less than half. Okay. So it is minus 1 minus L is less than half. Okay. So now what you are going to do is to okay. So if you add these two inequalities, you get this, right? Half plus half. So basically this is 1, right? So you know that it's bigger than minus 1 minus, sorry, 1 minus L plus minus 1 minus L. So this is basically equal to 1 minus L plus minus 1 to the power 1 plus L, right? So you factor out the minus 1. So but minus inside the absolute value is plus. Okay, so this is basically 1 minus L plus 1 plus L, right? So when you take the minus 1 out, it becomes plus 1. So it's basically 1 plus L. And here you get 1 minus L. Now you studied triangle inequality of absolute values in the first chapter, right? Absolute value of A plus B is smaller than absolute value of A plus absolute value of B, right? So you learn this. And so this is what we call triangle inequality, right? You studied in the first chapter. So you apply the triangle inequality here. So this is bigger than or equal to maybe right. So this is bigger than 1 minus L plus 1 plus L. Right. So when you add all of them, that becomes small because absolute value of A plus B is smaller than absolute value of A plus absolute value of B. That is the logic you are using. Right. So this is basically equal to 2. You can say equal. Triangle inequality. So they are equal. There's no harm in that. Right. So that is 2. So what you have here, 1 is bigger or equal to 2. And that is what you get, right? 1 is bigger or equal to 2. and that is obviously a contradiction, right? So you all know that 1 cannot be bigger than or equal to 2, so that is a contradiction. So if this is a contradiction, right? So this is contradiction. So if this is a contradiction, the assumption is wrong. So this sequence cannot have a finite limit, right? So that is how we prove that the sequence, a certain sequence do not have a finite limit. Right? So now let me come back to epsilon is equal to half. Why this half is chosen? And suppose you choose this as 1. Just for the argument, you choose this as 1. Right? So instead of this, if you choose this as 1, you choose this as 1. This is basically 1. This is basically 1. This is 2. So then this contradiction don't work, right? So that is why we choose epsilon is equal to half, right? So choosing half is important. So that means when you add these two epsilons, that has to be something smaller than 2, right? When you add these two numbers, this number must be smaller than 2. Then only you will get the contradiction. Otherwise, you cannot get the contradiction. So here you are making up the contradiction. So you are free to choose your epsilon. So that is why I choose 1 upon 2. If I choose 1 upon 3, it is fine. Because here I will get 2 upon 3, right? That is still bigger than or equal to 2 is a contradiction. So that is fine, right? So you have to be careful with the choice. You have to choose epsilon in a way such that you get a contradiction, right? So you always choose epsilon as small as possible. So here you choose half, that is fine. Okay? So this is how we prove that the sequence do not have a finite limit. And this part I leave as an exercise because you can figure it out, figure out the solution in the similar way. Okay. So that's a thing. So one more information with this, right? In these two sequences, you can see two patterns, right? So let me show you this. Right? So here in this sequence, you can see that -1 to the power n is actually -1 plus 1 -1 plus 1 -1 plus 1. It is oscillating between -1 plus 1, right? So that is why when you draw a small tube, right, the sequence does not fall inside the tube, right? So that is why you have not a finite limit. Actually, the sequence will not have a limit. Later on, we will study about that, right? So that is the -1 to the power n. N is, you all know, right? So this is basically 1, 2, 3, 4, right? So you all know it is 1, 2, 3, 4, 5. So it is keep on like going like this. So that basically you cannot find a place because as long as n increases, this keep on growing. Actually, it goes to infinity, right? When n goes to infinity, sequence also goes to infinity. That is why it does not have a limit. So here in this example, there is no limit. But here in this example, there is a limit, but the limit is infinity. Right? So these are the slight differences. But here, because we are talking about finite limits, let us stick with the finite limit. Now, let us say that we prove or we know the existence of finite limit. Then the question comes: how many limits are possible for a sequence? And if there is a finite limit, is there only one? or whether there will be 2, 3 or 4, right? Actually, it ended up like, right? So if there should be only one limit. So let me write this as a theorem. If there is a limit, then there should be only one limit. You cannot have two limits there for a sequence, right? So the proof is quite easy, right? Again, if you want to show there is exactly one limit, let us say there are two limits, right? Right, so let us say L1 and L2 are two limits, right? And basically, no, not greater than, you can say, and you assume that L1 and L2 are not equal, right? L1 and L2 are not equal, right? So clearly, then the difference between L1 and L2 is non-negative, non-zero. So obviously, absolute value of that will be positive. You all know that, right? So now what we have is this. Right, so limit of xn is equal to L1 means you can write the definition for every epsilon positive. Now with this limit, you have one n1, right? So that's for some n1. Now another one, you have limit n goes to infinity, xn is equal to L2. So that means for every epsilon positive, you have n2 belongs to natural numbers such that xn minus L2 less than epsilon for all n greater than n2. Right, so you have two definitions, one for n1, L1 associated with the n1 and n2 associated with the limit L2. Right. So now there are two things. You have n1 and n2, so you have to combine both of them and you have to fix an epsilon, right? So you choose because you already know L1 minus L2 absolute value is positive, you can choose epsilon as half L1 minus L2. And then you have two n's, right? N1 and N2. You have to combine them. So what you do is, always, it's easy to choose the maximum among them. Right? Choose n as the largest number among n1 and n2. Then for every n bigger than n1, sorry, n, you will get n greater than n1 as well as n greater than n2. Right? So you can have n greater than n1 and n greater than n2 as well. So now you combine both n1, n2, and also you have an epsilon. So basically, the two relationship can be combined as well. So actually, xn minus L1 is less than half L1 minus L2. At the same time, Xn minus L2 is less than half L1 minus L2, and it is for all n bigger than n. Because if n greater than n, then clearly n is greater than n1 as well as n is greater than n2. So obviously these inequalities hold for both L1 and L2, right? So that's what you have. Okay. So what you are doing now, what you are going to do is you are going to do this, right? Right. So if you consider this L1 minus xn plus 1 plus xn plus 1 minus L2, right? So this is actually L1 minus L2, right? So you all know that. If you start with L1 minus L2, you add and subtract x capital N plus 1 and xn plus 1, right? So that is because the result is true for all n bigger than n. So you can choose n plus 1. So this by triangle inequality, you know that xn plus 1 minus L1 plus xn plus 1 minus L2, like similar kind of thing. You take out minus first from this and then do all the things, right? So actually I combine two steps, first triangle inequality and also taking out the minus from this, right? So that is what we do. Now this is because of this is basically less than half of L1 minus L2, and this is again half of L1 minus L2. That is actually L1 minus L2. So what you have is L1 minus L2 is strictly less than L1 minus L2, right? So this is lesser equal, but here, yeah, strictly less than L1 minus L2, right? That is not possible. The same value cannot be strictly less than itself, right? So it can be less or equal, but cannot be strictly less than. So your assumption is wrong. So that means these two cannot be equal. Sorry, these cannot be not equal. So that means both of them are equal. So this guarantees that the limit of a sequence, if it exists, is unique, right? So that is the proof of uniqueness of the sequence. So I will stop here. In the next class, I will talk about infinity, the limit of the sequence being infinity and some other properties. Okay? So let me stop here and then continue tomorrow at 1.